And then I would like to say welcome everybody to come to this online webinar. And we will have this webinar talking about machine learning in astronomy and space science. And today we have our first speaker, Eleonora. She is a PhD student at Cardiff University, which is in Wales in UK. And I think it's your last year of PhD study, right?
Yes, that's right.
Yeah, and the supervisor is Dr. Cosmo Insera, who is also the PI of the ePestle Plus project. That's why I know Cosmo and Eleonora very well from this ePestle Plus project, which is we are the largest survey for the supernova and to classify and to follow up, observe all different kinds of supernovae. And today, Eleonora will tell us the insights into the supernova science using machine learning. So the talk will be like about 45 minutes, and then you are welcome to ask questions afterwards. You can raise your hand or leave your questions in the chat. So I think to welcome everybody again, can we watch the video from Mengze about this project? And then Eleonora will start. So this is the first topic today, and then next one will be in May and June. And then we will have summer break, and afterwards we see you again in September. And then today, very happy we have Eleonora as our first speaker. So talk begins. Okay. Thank you, Eleonora. Please share your screen.
Okay. Let me just get that up now.
Yes.
Okay, can everybody see that? Thanks very much for the opportunity to speak today. I'm very excited to be the one opening this talk. So today I'm going to be talking about machine learning and also my own research, and in particular, how to apply machine learning to solving a problem. So I'm going to start off with a bit of a background on machine learning. So in general, machine learning is training a computer to learn and train a computer to learn from data. And this is a very useful tool if you have a lot of data, more than you can process by hand, and you want to see if you can get information out of it. And there's lots of different kinds of data that you can work with for machine learning. So I've got some examples here. So for example, images, like classifying images or recognizing images, time series forecasts, so trying to predict how something like stock prices might change over time, working with text, like text translation, and things like that. So we're going to open with a simple example of a problem. So for example, you've got a garden filled with flowers, and you want your machine learning algorithm to be able to look at a picture of a flower and tell you what kind of flower it is. So there's two main types of machine learning. There's supervised and there's unsupervised. Where supervised learning is where your data is labeled. So it's being given the answers already. So for example, your training data is lots of images of flowers, and you told it what kind of flower each of those is. And unsupervised is unlabeled data, where it's learning without a teacher. Moving on to the next slide. For supervised learning, this is like what training data could look like. You've got lots of images, and you've got labels for it. And for these labels, someone would have to go through and label these by hand. So it can be quite an exhaustive process. On the other hand, for unsupervised data, if you've got lots of images and you don't know what kind of flowers they are, you can still do things with this. So for example, we've got anomaly detection here, where let's say that you've got lots of blue flowers and one red flower. It can recognize potentially that one is different. And also, for example, with clustering, it can be like, I don't know what these kinds of flowers are, but this type, and this type are quite similar, and you can form groups like that. So back to supervised and unsupervised. Classification and similar is in unsupervised, and clustering and anomaly detection is in unsupervised. And we'll be focusing on supervised learning today. So I thought I'd give you a second example. For example, predicting house prices. So this is something called regression here, where you're predicting a number based on a set of features. And this is similar to what we'll be looking at today, where the inputs you put into your machine learning code, you would say, for example, these houses have this many rooms, they're this big, they're this kind of house, and the output from your code would be the house price. So that was a quick background on the different kinds of machine learning. So machine learning in astronomy can be very useful because there's lots of data in astronomy, and there's lots of ways that you can approach applying machine learning. The example I have here is image recognition to classify galaxies, where, for example, classifying them as an elliptical galaxy, spiral galaxy, is something that generally one would do by eye, and machine learning can help you do this much more quickly and at much larger scale. But today I'm going to be focusing largely on my area. So I look at supernovae, and I'm going to start off with giving a bit of a background on supernovae in general. So a supernova is the explosion from a dying star when it reaches the end of its life. And there's lots of different kinds of supernovae. Something I'll be focusing largely on in this talk is core collapse supernovae in general. And this, if you imagine a star which is burning heavier and heavier elements in its core, and it begins to form these layers of different elements, like you can see in this figure. And as the star starts to fuse iron in its core, this requires energy rather than releases energy, and therefore it can't support itself against its own weight anymore, and it collapses. So this is the core collapse supernovae. However, there's lots of different kinds of supernovae, which are generally classified on its chemical composition. So, for example, if there's hydrogen or not. So if there's hydrogen, core collapse is one of the examples of these, where you can see hydrogen because of this outer shell of hydrogen is retained, and you can see signatures of that. But there's other kinds of supernovae as well. Type 1a is another well-known example, where this is formed from a binary system of a white dwarf and a companion star. And material is accreted onto the white dwarf until it reaches its Chandrasekhar limit, and then it explodes. So that's another kind. But there's also more exotic kinds of supernovae as well, such as superluminous supernovae, which are very bright and they can't be explained by, for example, a core collapse mechanism would not be enough alone to explain how bright it is. So this is a background on supernovae. So why is it useful to look at supernovae? So Supernovae are very bright, and there's a lot of variability in them depending on what kind of star explodes, what kind of environment it explodes in, and they produce very big shocks and lots of dust. So because they're very bright, they can be used as distance indicators or standard candles. If you can relate its brightness to its intrinsic luminosity, you can use that to calculate the distance, which can be very useful in cosmology. Because of the dependence on the progenitor and the environment, you can use it to track stellar populations and environments and track that through cosmic time as well. And the shocks and dust they produce, so heavier elements are formed in supernovae, and these are responsible for the chemical enrichment of the universe. And also their shocks can trigger star formation and compress the interstellar medium. So supernovae can be applied to quite wide areas of physics, and they're very useful objects to look at. So the next question is, what kind of data do we get from supernovae? So what would we have to work with? So largely we've got photometry and spectroscopy. So photometry is basically imaging of a supernova tells us how bright it is. And from a series of these images, we can calculate the light curve. And the light curve is just a measure of how bright the supernova is over time. So you've got some example light curves here, and a supernova would evolve over hundreds of days, and how its brightness changes also depends on the supernova type. And looking at light curves can give us information about like how much energy there is in an explosion, what kind of power sources could be powering it. It can also help us to find the explosion date, looking at the light curve and figuring out roughly when the supernova exploded, which is also very useful, knowing how old the supernova is. So on the other hand, spectroscopy, this gives us supernova spectra, and this gives us a lot more detail on the chemical composition. It can tell us about velocities, and spectra are usually what's used to help classify a supernova. For example, the presence or absence of hydrogen would tell you if it's a type 1 or a type 2. And also notably with supernova spectra, as the supernova evolves over its hundreds of days, the appearance of the spectra changes. As the supernova ejecta expands and cools, it becomes more transparent, so we can see deeper and deeper inside it. So we'll see over time, rather than, for example, hydrogen at the start, over time we'll start to see more of the metals inside. And again, in this figure, you just got some examples of different kinds of supernova and how the spectra could look different accordingly. What kind of problems do we have in the supernova area that could be helped to solve with machine learning? So machine learning could help to overcome some limitations of computationally expensive tasks. For example, I'll go back to the previous slide. Modeling can be very important because lots of these lines can't be uniquely identified. Sometimes they blend together. Lots of different elements can produce similar lines in similar regions. And one of the best ways to try and find out what's going on in a spectrum is through modeling, where you use physics that you know, and you try out different elements and different velocities, and then you compare the model spectra to existing spectra to see how well it matches. But again, this is very, very computationally expensive, and this is an area which you could approach to try and make that easier with machine learning. Another problem can come from the fact that there's a lot of supernova targets and there's limited resources to follow up on them. and machine learning could help to select which targets could be most scientifically suitable to follow up on. For example, through anomaly detection, you could see this looks like it's going to be an unusual supernova. So let's flag this one for being worth detailed follow-up. Also, useful things to try and make easier would be to classify supernovae using machine learning as well. This is just another way to be able to help make it easier to process a large number of targets. So here's back to photometry and spectroscopy. So modeling would generally apply to spectra. You can classify both light curves and you can classify both spectra as well. But what I'm going to be focusing on for the rest of the talk is going to be on what I've been doing specifically on predicting the evolution of supernova spectra. So I'll just go back here to show you the spectra again. So these spectra change over time. And often we don't have resources for spectral follow-up or to get spectra at every stage of its evolution. And there's also lots of supernova targets where we might only get 1 or 2 spectra. And there's a lot of information that we're particularly missing there because spectra have a wealth of information on chemical composition and on velocities and on temperature and many other things. So my idea here is to try and use machine learning to try and take the information that we have and also the information of lots of example supernova spectra and try and see if we can fill in that information. So this is something that I'm going to be referring back to as I go through what I've been working on. This isn't a final one by any means, but this is just an idea of some of the steps that you might go through when you're looking at tackling a machine learning problem. So first of all, you would identify your problem. So in this case, it would be trying to fill in missing spectral data to get a full spectral evolution. And then the next step you'd do is you'd want to gather training data, and you want as much data as you can get, as much high quality data as you can get, because your algorithm is only as good as the data you train it on. And once you have your data, you want to identify some features. So you want to identify things that you can use to learn from. So for example, for our house prices, features would be the number of rooms, the size of the property, the location of the property. So yeah, that's identifying the features. And then you want to clean up the data because the data might be messy, there might be outliers, it might be noisy, and you want to make sure that it's all in a format that you can use to put into a machine learning algorithm. And then once you've got this and you've got the data already, you want to decide what kind of machine learning you're going to use. So you want to choose an algorithm. And then after that, I've put train test split in here, where basically you have your training data and you split it up and you use some of it to train your algorithm, and then you use some of it to test the algorithm which you've just trained. And then you want to train your model, and then you want to test your model, and then you want to evaluate. You want to have a look at how well your machine learning algorithm has done and look at how well it solved your original problem and see what kind of changes you might want to make. So you might want to get more training data. You might want to look for different features, or you might want to change your algorithm. So it's always a process of going back, looking at how it does and seeing how you can improve it. It's a continuous process of improving. So I'll start going into some more detail. So I'll start off with how I gathered data. So in order to train some machine learning, we want some good quality spectra. And we want as much spectra as we can get from as many supernovae as we can get. Ideally, we could have lots and lots of spectra for each supernova, just to have as much data as possible. I mentioned earlier I'll be focusing on core collapse supernovae. It's because different kinds of supernovae have different physics. So it's best to be consistent because it's giving our algorithm more of a chance to learn. So I'll be looking at type 2s. And we'll want spectra from a range of phases. So if a spectra, if supernova evolves from explosion to hundreds of days afterwards, we want a range of spectra throughout that time. And spectra which have been published, which have appeared in papers, you know that those are high quality spectra, so those could be good to use. And I sourced almost all of my spectra from the Wiseman Supernova repository. And this is a good public source for spectra. So it's all accessible to the public, and published spectra are uploaded there. And there's many thousands of spectra that you can use. And I've put here again that the model is only as good as the data that trains it. So this is quite an important stage. So the next thing is we're going to see what features we can identify from these spectra. So it's a busy slide here, but there's some basic things that you can measure from spectra. And I've got some examples of spectra here at the bottom. So you can measure temperature from a spectrum where you fit a black body to the continuum. This isn't a perfect way of measuring temperature, but it can give us an approximation. And you can measure velocities of lines. I've got an example here of measuring the velocity of hydrogen, where you can see you've got this profile here. And if you find the minimum of this line and compare it to the rest wavelength at which you'd expect it to form, then you can work out through Doppler shift what velocity the material is moving at. So this is information that you can measure from the spectra. And also phase or epoch is going to be very important here because that tells you how old this spectrum is. So how long since the explosion date has this spectra formed. And the explosion date is, like I mentioned before, something that you find from the light curve. So you can see when the explosion started. So on this scatter plot here, I've got 4 different parameters. So we've got epoch, which is the phase, and we've got the temperature, and also the velocity of 2 different lines. So I've taken the velocity of hydrogen, and I've taken the velocity of iron. And these are just velocities of 2 different lines to give us an idea of what the supernova ejector looks like. And I've also got some correlations with these parameters here between them, so you can see what kind of spread of values that we have. So this is some features that we've identified. So let's move on to how we're going to clean our data and get it ready for machine learning. So we need to standardize the data that's going in. So we want all the data to be the same shape. So first thing we'll do with our spectra is, this is one that we might have. There's quite a variable wavelength range. Some of the spectra were between 3,000 and 10,000. Some of them were different. And we want to make sure that those are all the same. And also we need to normalize the flux. So we normalize the flux between 0 and 1. Take a standard wavelength range from 4,000 to 7,000. We chose this range to include key features such as the hydrogen and the iron, while keeping as many spectra in our sample as possible. And also the spectra are smoothed to try and remove some of the noise and try and take the features without worrying about any other noise that might come into it. And so the next step would be to choose an algorithm and train it. So the first method that I'm going to talk about is, I call it the parameter method. And that is going to be using these features of temperature, velocity, and phase. And I'm going to try and use this to predict spectra. So the first step for this is to try and use the phase, the velocities, and the temperature of a spectrum and use it to recreate the spectrum. So it's basically going from 4 data points to the full 200 data points of this spectrum. And I did this using a neural network. A neural network is designed to function a bit like the neurons in the human brain, where you'll have your inputs and you'll have your outputs, and you'll also have some hidden layers. And these hidden layers basically assign weightings to the input. So it transforms them, adds some weights, and then it converts that into an output. And as you train your neural network, it goes back and forth between the input and output. So it goes through the layer once, it compares the output from the neural network with the example output that you've told it should be like. It compares the two, and then it goes back through backpropagation, it updates the weights, and it improves the neural network. So you'd want to go through it quite a few times as it trains. So here's some examples of some predictions compared to the observed spectrum. And again, how this was done was for each observed spectrum, you measure the phase, the velocities, and the temperature, and then you put that into your neural network and you get a spectrum out. So as you can see, the observations and the predictions, they can match quite well. It can reproduce the figures and the shape of the spectrum well, so that's good. However, these predictions are for the same phase as our observed spectrum. So we need to take one more step. Here in testing the model, what we want is we want our temperature and our 2 velocities, but we want to get these parameters at the time that we want to predict, rather than the current time for the spectrum. And this is a setup where you need more than one spectrum to make your prediction. So I'll talk you through these figures. So in this situation, these are our parameters for the temperature and the velocities, and the black points are our spectra. And from all of these spectra, which are also shown in this figure on the right, the black ones are our spectrum. And we randomly sampled 12 of these spectra. So of these points, randomly take 12 of them, and we did this 50 times and tried to fit a function to them. So you can see on here, the blue lines are functions being fit to any 12 of these points. So it's done 50 times, just to see also how much of a difference it makes which spectra we're using to do this fit. So, and once we have a functional fit to the temperature, to the 2 velocities, we can then use this function to pick any time, let's say 50 days, and have a look at where the blue line tells us that the temperature or the velocity would be. And that's how these predictions are done on this other figure. So we have our black spectra, which are our observations, and the green spectra are our predictions. based on the blue lines here, the functions that we fit to the values of the spectrum. And these predictions have been made every 3 days from 15 to 81 days. And all 50 predictions for that time are on top of each other. And we can see that for 12 spectra, the predictions, the green matches the spectra quite well, and there's not a lot of variation depending on which 12 spectra to use. And the biggest uncertainty that you get is at the early times here, so in the first 20 days for temperature. And you can see that the earlier spectra here have more variability. So here's the same figure again, except here we've taken 4 random spectra instead to do the fits. So for example, this first figure, we take like 1, 2, 3, 4, and then we do a fit to that. And you can see that depending on which spectra are used to make the fit, it starts to get a lot worse. Some of these fits go very wrong here. And this could happen if, for example, you take 4 spectra which are very closely grouped together, and then it struggles to fit that function. And if you have a look correspondingly on the other figure of the green predictions, you can see that there starts to be a lot more variation depending on which spectra you've used. It still matches the predictions quite well. Especially at later times, you can see that most of the spectra are quite good at reproducing the features, but some of them here are going quite wrong, and likely corresponds to places where these fits are much worse over here. And finally, I'll show you for 2 random spectra, where here you can see that it starts to get very messy. I will say that good predictions are still possible, but it can start to go quite badly. And you could say at this point that for 2 spectra, it's not really viable to make these predictions. So we can evaluate here now. And the problem is that, like I mentioned before, in a lot of cases, there might only be a couple of spectra. And as we can see, for a couple of spectra, this method would not work well in predicting the full evolution. If you have lots of spectra, if you've got 12 spectra, then you can fill in the gaps with this method well. But you've already got lots of spectra anyway. So you already have an idea of the evolution. So this method would be less important in this case. We'll evaluate and we'll try something else. And we'll have a think about how we could try and approach this problem to predict evolution from as little as maybe 1 spectrum, so with little information. So we can consider gathering more data, we can consider the features that we use, and we can think about the algorithm which we've used as well. So let's have a look at using a different algorithm. So once again, this is back to using a neural network like before, except this time, let's think about the inputs and the outputs that we're going to put into this neural network. So we want a spectrum at any time. So our output needs to be a spectrum. And our input needs to include the phase at which we're requesting the spectrum. And we also need to input information about what we know about the supernova already. So information about the 1 spectrum that we're using to make the prediction. So how about giving it the whole spectrum and also the phase at which we want the new spectrum. So let's consider the data that we have and how we could turn this into a training set. So let's say that we have Supernova 1 and Supernova 2. And Supernova 1, we have 3 spectra for it. One at a phase of 10 days, one at a phase of 30 days, and one at a phase of 50 days. And let's say we're starting with our spectrum at 10 days. And that's all the information that we have about the supernova. And we want to use that to predict the spectrum at 50 days. So what would we give the neural network? We'd give it our spectrum at 10 days. We'd say this spectrum is at 10 days. And we'd say we want the spectrum at 50 days. So the input would be spectrum, 10 days and 50 days. And the output would be our spectrum at 50 days. And we've got Supernova 2. So we can do the same thing here. For 48 days, we want the spectrum at 25. So we'd say, here's the spectrum, 48 days, give me the prediction at 25 days. So this is how the input and the output would look. And what we would give for our training data is, if these are the supernovae that we have, we can match it up. So into the training data, we'll give 10 days to 10 days, 10 days to 30 days, and 10 days to 50 days. And likewise for the other one. And then we can just pair that all up. And this way, we end up with a lot more data than we originally had. So it's kind of augmenting of the data, and it's getting as much information out of what we have as we can. So the next thing to do here is to test this and see how it does. So this figure here shows the predictions from this neural network. So we've got 6 different panels here. And in each of these panels, we have the black spectra, which are our observed spectra. And we have the orange spectra, which are our predictions. So it's quite similar to these images here. We've got the predictions and we've got the actual spectra. And the reason that we have 6 panels is because for each one, we're using a different one of the observed spectra to make all of the orange predictions. So, for example, we've got this spectrum here highlighted in blue. And from this spectrum, we could say, here's the spectrum. This spectrum is around 50 days. Give me the prediction for 9 days. And then this would give us this one. I could say, here's the spectrum at 50 days. Give us a prediction for 40 days. And then we have this orange one. So, and this is the case for each of these panels. So here we're using this spectrum, this blue one, to calculate all of the orange ones. Here we're using this one to calculate all of the orange ones. And in each of these panels, we can compare our orange predictions to our actual spectra, which are the black ones, to see how it compares. So on the face of it, it looks like this is doing quite well. We can see that the predictions are matching up reasonably well with our observations. So this is looking good. But how can we measure success in detail? So we want our predicted spectra to be able to reproduce the key lines. So looking at how well it matches with our hydrogen or with our iron, which are the different wiggles you can see here. We also want to see how well it reproduces the velocities and also how well it reproduces the continuum. So how much of the overall shape it reproduces as well. So having a look at velocities, we've got a figure here for measuring the hydrogen, and this is for measuring the iron. And I've got 2 different ways of measuring the velocities here. Don't worry too much about that for now, because it's not really important. But essentially, our solid lines here and the colored region is our predictions. So I've got it both in blue and both in orange. Those are just 2 different ways of measuring the predictions. And the points here, the black points and the red points, those are the ways of measuring our observed spectra. So again, there's two different ways of measuring it, but the orange matches to the red and the black matches to the blue. And from these figures, we can see that for this supernova, the velocities here match up quite well. So that looks like it's doing well. But the next question that you could ask here is, what if we don't know the explosion date with accuracy? So what if we think the explosion date is one date, but it's actually 10 or even 30 days off? So we've got 3 panels here. So this is our original panel on the very left side. The middle panel has 10 days shift. So we've just added 10 days onto all of the phases just to say that we're 10 days off from measuring the correct explosion date. And this very right panel here, we've added 30 days. So the first thing to notice is that for this end panel here of 30 days shift, the uncertainties start to get a lot bigger and the velocity predictions are not looking as good. Although if you look at it closely, for example, this iron one here, let's say we look at 40 days and then have a look at, for this black point here, at what point this black line matches up with it. So if you go across, it's about maybe 70 days. So the velocities themselves are also shifted. So this could even give us an idea of the correct explosion date. For 10 days here, the difference is a lot smaller, and it still seems to manage to do the prediction reasonably well. So another test here is to try and make predictions for a more unusual supernova. So this is predictions for 2005 CS, and this is a low energy supernova. So it's slightly unusual in that respect. It evolves at a different speed, and the velocities are lower than you would expect. So it's different from the kind of supernova that it's generally trained on. And you can see that this is a case where the predictions work much less well. If you look at how well it matches up, if we use a very early spectrum, so the blue spectrum is quite early on, then the later predictions are not quite right. You can see that the lines here, there's a big shift. So it's not being able to predict that correctly. And in places, it doesn't match up too well in terms of the shape of the features either. When we're using quite a late spectrum to make the predictions, so this blue one down here, then the spectra closer to it match well. The lines are a closer fit, except for the very early ones, where it starts to not have the continuum as well reproduced. And this profile here is just a different shape in the predictions. And if you have a spectrum around the middle, like this blue one here, then both the early ones and the later ones are a bit better. Neither of them are perfect, but it's a bit closer. So also this tells us that depending on what time the spectrum is that you're using to make all of the predictions, that changes how well it performs. And so it's time to evaluate and see how one method compares to the other. So
yeah, you have 5 minutes reminder.
Okay, perfect. Thank you. So let's look again at what ways we could improve this method. So we could go back like we did before and try a different method, or we could try a different algorithm. But I think that one of the biggest things that could help improve this is more training data, because the more that we have, for example, if you look back at this supernova. If you have more supernovae that are similar to this one, then it could help it better recognize how to deal with this kind of spectrum when it's given to the algorithm. So that's different ways that we could improve it. And I've just added this slide in here about further applications of this method. So like I mentioned before about standard candles, this requires calibrating the luminosity of the supernova to how bright it appears. And if you look at a supernova and you know how luminous it would be, then you can compare it to how bright it looks, and you can use that to calculate the distance. So it's generally, this is used for type 1A because they can be well calibrated. But it's possible to do the same with type 2, like we've been looking at here, if we have good knowledge of the light curve and also the velocity. And if we can predict the velocity of these spectra using our spectral predictions, then this could be helpful, perhaps, for this method. Also, this method could be useful for population studies, where you have lots of different supernovae and you want to compare them at the same phase. And in this case, you could request this algorithm to give you spectra at whatever phase you want, so you can more easily compare different supernovae. And it's important to get them at the same phase because there's different physics at different times. And it could also be useful for creating spectral libraries. So having more examples of how a spectra looks at this time or that time to also still help to make comparisons. So the conclusion is that method is a work in progress, but it could be promising for a new era of surveys where there's an unprecedented number of supernova candidates and we can't follow them up with spectra. But maybe with this method, we can use the few spectra that we have to try and get more information about how this supernova would look like if we were to take more spectra. So in summary, machine learning can help to process large amounts of data and find trends, patterns, and relationships, and it can be used to shortcut computationally expensive work done by humans. And I focus just on my area here, but it can be applied to many areas of astronomy. And I've got this slide in here as well, in case, as I know many of you are students, in case you're interested in applying machine learning to your own research or learning more. So just quickly, I'll say that Python is a very useful language to learn because it's got a lot of pre-built packages for machine learning like sklearn and TensorFlow, and these are very easy to use. Jupyter Notebooks is also very useful as a way to present your code. And another recommendation I'd give for an introduction to machine learning is Kaggle. This is an online free website which has data science resources with beginner notebooks and data and problems. So it's a good way to get started as well. And also to go to more conferences and talks and hear other people talk about machine learning. So thanks very much for listening, and I'm happy to take some questions.
Thank you so much for your great talk. And we already get questions. Sorry, I don't know how to pronounce your name. So
Hi, I can speak up.
yeah.
Thank you, Janet.
Yes.
My name is like Surojit Saha. Thank you. Yeah, Surojit Saha. So thank you, Eleonora, for this wonderful presentation. I've got some couple of questions. You mentioned that in the temperature region or temperature regime, the performance was very poor in reconstructing or recovering your spectrum. So is it due to the lack of training data or or some issues with like the neural network? What is your opinion at the moment for this?
So were you talking about this slide here?
It's probably yes. Yeah.
So A big part of it is indeed the lack of training data. Although the biggest problem in these cases was just because of the uncertainty in what the temperature actually was at the phase where we wanted to make the prediction. So for these early, I'll show you this one because it's this one's better. For around 20 days, you can see that predictions for 20 days, as you made the prediction 20 times, there's lots of spread in the shape of this spectrum. And looking correspondingly at around 20 days here, there's also a lot of spread in what it predicts the temperature to be. And between 5,000 and 10,000, it's a very big range, which is why lots of the predictions would have differences in how they end up looking. So the main problem here is that there's too few spectra that we're using to fit a function to it. So it's just a lack of information, because if you look at when you have 12 spectra to fit this function to, then it performs a lot better. So in a sense, it's down to the limitations of this kind of method as well. I hope that makes sense.
Yeah. Thank you very much for the explanation. Yeah, that's what I also assumed about the lack of training data could be the one reason you have not exactly like satisfying result in the temperature region for the early days. Yeah, but however, I think once you have another few observations of supernova, probably in which region you want to look, for example, the early days of the supernova or some late time evolution where you mentioned that after the ejecta gets more like more transparent. So which would be more area for you to focus on?
So in terms of which method, I do definitely think that this second method is the more promising one. And I also agree that more training data, both at earlier times and later times, to an extent, would be very useful. Especially if you're looking at this one here, you can see that the predictions earlier on are less good. And we do also tend to have less spectra taken at very early times, because sometimes it takes a while to spot the supernova and then to take a spectrum. So more spectra tend to be in later phases. So as we get more and more data, especially from upcoming surveys, which promise to deliver very large numbers of supernova candidates, there's going to be more and more data to train machine learning algorithms from. In terms of later data, at some point in the supernova evolution, it changes into a different kind of physics regime, which is called the nebula stage, where the physics changes. And at this point, I think that it would make more sense to switch to a different kind of machine learning algorithm, because it's a different kind of physics and it could just confuse the algorithm. So generally the cutoff for this data here was around 100, 150 days. Hope that answers your question as well.
Yeah, thank you very much for the answer. Yeah.
Thank you. So we take the other question. So the other question is, how do we clean data? How much experience comes into play while cleaning? I think this question when you show the slide of your machine learning pipeline.
This one here?
Yes, I think so. So the question is, how do we clean data?
So I've come back to this slide because this is the example of how I've cleaned my data. But going back to the machine learning pipeline, in a lot of cases, most of the work in machine learning comes from preparing your data and trying to figure out how you're going to put it into the machine learning, because there's lots of easy algorithms to access through Python packages. So most of the work, in my opinion, comes in this stage. And in terms of getting your data ready and cleaning it, you need to consider what form you can put it into your algorithm. It all needs to be the same shape. It generally needs to be normalized. You need to think about how you're going to address outliers, whether you want to include them, whether you want to exclude them. You need to figure out how you might deal with missing data. Do you want to fill in the missing data with averages, or do you just want to remove those cases altogether? So it's definitely a case-by-case basis, depending on what problem you're looking at. It's definitely something that you will be spending a lot of your time thinking about, both identifying the features and cleaning the data. I hope that answers your question. There's also probably out there on the internet lots of examples of cases of people working with data similar to you, which can help give you ideas about how to clean it as well.
Yes. Yeah. And there is the other questions about, is there the tutorial about spectral analysis using machine learning?
I'm not sure. I don't think there's one single obvious tool. I think there's plenty of papers out there on the topic. So I guess all I can suggest is to have a read around and see what you can find.
Yes, or such machine learning courses now seems required due to now people are so interested in this topic. So maybe Yanchen would know better if NCU has provided such lectures.
Yes, there's lots of resources out there to help you
Yes.
like practice and learn more about it.
Yeah, and your final slides also show some places for students to learn.
Yeah, I do particularly recommend Kaggle because I found it quite useful. There's also just lots of free data sets on there and lots of examples as well about how to approach problems and go for it for different kinds of data. So that's very useful as well as a starting point.
Thank you. So the other question is about, do you split your data randomly or evenly pre-type of supernovae? Do you also follow the 9:1 trend and test ratio?
So this is about the train test split, I guess. You definitely want to split it randomly. You want to make sure that you've shuffled it, because if there's any bias in how you split your data, then you might risk something called overfitting, where you train your algorithm very specifically for the data you have. And so it doesn't do as well on data it's not seen. For my case, I didn't use 10% test, 90% train. And also for this method here, the train test split, I split by supernova rather than by Spectra, just so I'm because if I'm taking it by Spectra and I've already trained the algorithm on some Spectra by the same supernova, I thought that could introduce some potential biases there. So I tried to keep them different. I hope that answers your question.
So they want to ask, how many supernova spectrum do you have in total or per supernova type?
So sorry, I didn't include it in my slides anywhere. For this first method, I had 700 spectra from about 130 supernovae. And for this second method, I had 1,000 spectra for around 150. So I got a few more. I also did some balancing as well, which I didn't mention, where basically there was a bit uneven in terms of there was lots more data at certain, so lots of like spectra in the middle and less spectra earlier and later. So something I tried to do to balance that out was to duplicate some spectra for cases where there weren't very many examples, which is called oversampling, where you're just trying to make an effort to balance it out. Because actually balancing your data is also very important. I would probably put that in the clean data stage of this pipeline here, because if your data is biased towards all of the spectra are at early phases, then your machine learning algorithm is also going to be biased, because then it will perform predictions better for the times where you have more data existing for.
Yeah, I see. Okay, so last question, due to the time also. So could you provide an accuracy score, like the recall score or residual perhaps, for your predictions? What's your criteria to consider that the prediction is satisfied?
So something which I did measure for comparing the spectra to the predictions was the mean absolute error, where at each point in the spectrum, I had a look at how much difference there was, so basically the prediction minus the actual spectrum. And then I took an average of that to try and figure out roughly how much of a difference there was between the spectra. So that was a metric that I looked at as well. Again, I didn't include that here, so sorry about that. But that was I thought that looking at the velocities is actually one of the more useful things to do here, because it's actually considering about how these predictions are going to be used. And these predictions have been used where you would start measuring properties from these predicted spectra, like the velocities as well. But that is also a way of considering its performance. With neural networks, it doesn't come with a score itself. You do need to calculate that, but for something like a random forest, which is a different algorithm, it can actually give you scores for how important all of the features are and how much they've contributed. So there's lots of ways to evaluate performance outside of what I've shown here, both for neural networks and other algorithms as well.
Yes. So thank you. And I think we are 6 minutes past the 10. So even we have more questions, or do you think you can answer this very quick? How do you select the input features?
So this is something of a case of trial and error. Basically, you try and think about your problem, think about the physics involved, and just try and make sensible ideas about what you can use as inputs. And then it's the case of what I mentioned before about going back and evaluating. So you have a look at how those features, those inputs you've chosen perform. And if it doesn't perform well, you can go back and choose different ones.
Yeah. So yeah, thank you so much. I hope the audience would ever ask question or satisfied. And we have a very wonderful 1 hour talk, and then introduce all of us about machine learning, how to apply it to study supernovae. And I think we want to thank you again, Eleonora, for your wonderful talk and prepare those rich information for us. So thank you again. And Yanchen, do you want to say something to close the webinar?
Well, yeah, I don't have much things to say, but just thanks again. That's really great talk, and I also learned a lot from from your talk. Yeah, I'm also doing Supernova, so I think it's very helpful.
Yes.
Thank you very much.
Yes. So thank you, and I think that's us today. And thank you for all joining. Thank you. So bye-bye.
Yeah, thank you very much. Yeah.
Thank you.
Okay. Yeah, goodbye, everybody.
You have a nice day.
You
Thank
too.
you.